the singular values show the strength of each of the concepts. A, as we said before, so A here, relates the concepts to the features, so they are somehow the new unit vectors, the new basis, as we know it from the eigenvectors of PCA. Yeah, so they are somehow related to this eigenvector. The eigenvector unit vectors here of PCA, and O relates the concepts to the objects, as we said, so they can be somehow interpreted as projections on the new bases that are specified by A. Yeah? So those guys here give you, well, we have three new bases, so to say, three new directions, unit vectors, corresponding to the three concepts here. And if we project the first Joe, the first guy here, on the first axis, we will get this one here instead of 1. Yeah? And this is the value of the second component, and this is the value on projected on the third component. Yeah? So those are the new principal components, in quotation marks, of course, so the new unit vectors, representing the new concepts. Yeah? Those are the strengths, the energy, the singular values, so somehow the eigenvalues in some sense. And this is actually the dimensionality reducted, well, the data set that we get if we project the original data set on those axes here, which are specified by A. Okay? Yeah, so that's basically it. So, well, how to reduce dimensionality? Well, we can, of course, use just O, but sometimes, as I told you before, K is much larger than D, or at least just a little bit smaller than D. It can even be larger than D, can be up to N, as I told you before. So how to reduce dimensionality? Well, we know that the singular values somehow tell you how important the concept is, and intuitively the third concept is not so important. So how can we get rid of this third concept in order to reduce the whole thing to 2 dimensions? And well, that's the basic idea. So we just set the smallest singular values, or the smallest singular values, can be more, to 0 in S, which eliminates the corresponding columns in O and rows in A. So if we set this one to 0, the corresponding row here in A, which corresponds to the axis representing this concept, will be deleted, which means that the corresponding column here in O, the last one here, will also be deleted. So we will end up in a 2-dimensional space representing the original 5-dimensional space if we omit the third column here, the third concept here. Yeah? Which makes sense because the singular value is very small compared to the rest. Yeah? So how many, or when is that sensible? How many singular values should we retain? Is there a rule of thumb? Of course, yes. So we try to retain enough singular values to make up 90% of the total energy in S. What is the total energy in S? Well, if we sum up the squared singular values, so 12.4 squared plus 9.5 squared plus 1.3 to the power of 2, the sum of the squared singular values is the total energy of this matrix here, of the singular value matrix. So yeah, energy is, so that is the example here, which sums up to 200 something. So if we omit the third one here, the retained energy is just summed up by the remaining ones here. Those two here, which is still pretty close to 245 something. So if we just omit this one here, we still keep more than 99% of the total energy. So we can easily omit the third concept here and reduce the whole thing to a 2-dimensional thing. Yeah? In this example, I won't reduce it anymore, but it's already reduced. Yeah, so it's already a two-dimensional data set. Here, in this case, we can even reduce it more than 2k to the rank here, but we can even get rid of this third concept, this third dimension, which somehow doesn't make sense. Or I mean, it's there, but the impact on the total energy is so small that we can easily reduce it. So the loss, again, the information loss we do is neglectable in that case. Okay, so if we don't want to have any information loss, by the way, we keep all the single values. So if we reduce this data matrix to this one here, we don't lose anything. That's just because this one here is a very, very artificial case where we have a lot of redundancies here, which is reflected in these two concepts here. So in this case, we just get rid of the redundancies if we take this representation instead of the original ones. But we don't lose anything in that case. Yeah. Here, if we omit the third one, well, if we take this one here, we also don't lose anything. If we omit the third one here, just take the first two here, then of course we lose. We get some information loss. But we don't lose too much, obviously, yeah, as the numbers suggest. So now the interpretation. So why is PCA a specialization of SVD? Well, if we have a look at the PCA, well, we can apply SVD. Well, PCA is actually applying SVD on the covariance matrix sigma, which is the data matrix, the normalized data matrix transpose times D. Yeah. Why is that? Well, SVD means that we decompose the original data matrix into O times S times A transposed. That means if we just take this formula and fill it in here, so we have the sigma, the covariance matrix is, as we said before, D transpose times D. So D is O as A transposed, so D transposed is O times S times A transposed, yeah, times D is times O times S times A transposed. Yeah, we just filled in for D O times S times A transposed, which is absolutely fine because we can do that with SVD. Okay, so then we just have to be, I have to rearrange a little bit, recompute a little bit. So the transposed version of this one here is just taking all the transposed versions of the multiplication here, change the order, and then we have A transposed now comes down to A times S transposed times O transposed. This is the first, these are the first three one here, and then we have the remaining three ones here is O times S times A transposed. The brackets are just to show you that we have the inner product here, which is the first multiplication which we will perform, and since O is an orthonormal matrix, O transpose times O is just one, it's just the identity. Yeah. If you don't remember that, just look up your relational algebra books. Yeah. So that means this one here comes down to well, we can just omit O transpose times O because it's the identity. So it's only A times S transposed times S times A transposed. So the brackets again should show you this is the first multiplication we have to perform. Well, S is a diagonal matrix, so the transposing has actually no effect. So this term here comes down to A times S squared times A transposed, and S squared for the diagonal matrix, it's just the squared entries in the diagonal. Yeah, so S squared is nothing else than lambda 1 squared, lambda 2 squared, and so on and so on. And this here somehow reminds you of something. Yeah, well, PCA gives you the eigen value matrix here in the middle, and the A is, we termed it V, is the eigenvector matrix. Yeah, and that's exactly what happens. And A, as you remember, is what is A? It relates the concepts to features. So this is the new basis, the new unit vectors that form the basis. And that's exactly what the V's are also do, the eigenvalues, the eigenvectors, sorry, are also do. Yeah. So yeah, A, relating the features to concepts, corresponds to the matrix of eigenvectors, obviously. The eigenvalues of the covariance matrix sigma are obviously the squared singular values of D, because we just got S squared here. If we perform SVD on the covariance matrix, we just get as the eigenvalue matrix, sorry, the squared singular values. So the eigenvalues of the covariance matrix are the squared singular values of the data matrix. So what does that mean? Well, eigenvalues and eigenvectors of the covariance matrix can be determined by SVD, so performing SVD on the data matrix instead of performing PCA on the covariance matrix. Yeah? So in other words, SVD is a method to perform PCA, but SVD directly works on the data matrix, whereas PCA works on the covariance matrix. Yeah? Okay, so yeah, why is SVD good? Well, SVD is sometimes a better way to perform PCA, especially if you have large dimensionalities. In that case, these numerical algorithms we talked before, we've seen also in action in the previous section, they may be challenged. Yeah, so for example, for text data, if you have 10,000, 20,000 of dimensions, then SVD is very often much more stable than PCA, because for PCA you have to perform or compute the covariance matrix first, and that may give you a lot of numerical insecurities, inconsistencies, and so on. And yeah, so SVD can be a better way to perform PCA here. And also SVD can cope with dependent dimensions. So we are not looking at D originally, but we are looking at, in SVD, at the rank of the data matrix. And so any K which is not D, especially if it's smaller than D, for SVD that's no problem. That's the normal case. For PCA, that's not the normal case, because you may run into non-negative or negative matrices which cannot be decomposed then. So in that case, SVD is the only way to perform that, actually. Yeah? And the other numerical algorithms may fail in that case. Yeah, so that was actually singular value decomposition, and yeah, as next chapter we will have a look at kernel PCA.